We will start by discussing a bit about the components of the of a typical micro PIV system. Although most of it has been discussed by Professor Basu in his lectures on PIV, but for the completeness, we will just discuss it in brief. So, the first and the most important thing, the seeder particles, which are used to basically track the fluid motion. Fluid can be anything, gaseous or liquid, as we have discussed, and we will be discussing a lot more about it in the upcoming lectures. So, this is one of the most important components, and it has to be chosen very wisely. For example, you can choose polystyrene particles of very small nanometers. It can go till 1000 nanometers also, and you can also use oil droplets of 1 micron size. Then the illumination system, basically to illuminate the region of interest, and in case of micro PIV we are more concerned with a volumetric illumination, which will be discussed later in detail. So yeah, this is very important, and there are a lot of illumination systems, but however lasers are the most widely used illumination systems because of the ability to emit monochromatic light, and they are highly collimated lights with very high energy density. And one of the advantages is that we can easily turn a laser into sheets for recording. And but in our case with say micro PIV, this sheet doesn't work, which we will discuss later. And the usage of semiconductor lasers like ND-YAG and ND-YLF are very commonly used, and they can actually deliver a large source of light energy in a very few nanoseconds, which can help to take take images of very fast flows even in micro channels. The camera, obviously, to capture images of the seeder particle, we need to have a appropriate camera system, which can be a high speed camera. And the synchronizer to control the timing of laser illumination and camera acquisition, and in our case mostly we use a PTU, that is a programmable timing unit. And finally you should have a computer or anything where you can actually take the data, store the data, and ultimately take it to the processing part. Now we will discuss briefly the working of a typical micro PIV. So this is how a typical micro PIV setup looks like. So if we start from this light source, you can see this light source can be pulsed or continuous as needed, and the capability of the light source, obviously you can see a laser passing through a diffuser plate, and this diffused laser light falls on this mirror, and this light reflects at this angle through this microscope objective, which you can modify as needed, and it goes to the micro channel. You can see this micro channel, this is the inlet, say this is the outlet, and you can see this particles also, and these particles are basically fluorescent particles. Now when this green light falls on the fluorescent particles, it emits back the fluorescent signature, that is, say, the red light. So this red light is again emitted through this system, and now it again comes back to this mirror. Now this mirror is a special mirror, that is the dichroic mirror. A dichroic mirror has different properties for different kind of wavelength. So mostly they are used for filtering and splitting or combining of lights, and here it is actually filtering, and it is not reflecting this emitted light, but it is actually letting it pass through it. See, you can see only the fluorescence emission is coming out through it, and it goes through a lens, and then it directly hits the camera chip, the sensor, and this is your camera. And this camera and this light source is basically controlled by a synchronizer, as discussed previously, and the data from the camera goes to the PC. So this is basically a typical working setup of a micro PIV. This kind of micro PIV is also known as epifluorescence micro PIV microscopy. And so the main principle is that the light emitted by these tracer particle is collected through the same window here, and the configuration is many a times known as a backscattering configuration. So now another interesting thing is that if we zoom in at this region, you can see that you find a focal plane, but we are actually illuminating a volume. So there is something known as the depth of correlation. So we will be discussing a bit more about it in future slides, but to give a brief idea, within this depth, basically the particles which are illuminated contribute significantly to the correlation peak, and beyond that we neglect the particle illumination and ignore the signatures coming from the particles. So this is another setup where you can see it's basically an alternative to the micro PIV which I showed previously, where you can use an inverted microscope also to do the same kind of PIV. Now here you can see one of the inverted microscopy setup with microchannel sitting at this place, and this is the power supply for mercury burner, and this is the lamp housing for mercury burner, and we are using this mercury burner to generate fluorescence light. Then you can see the microscope light source here from where this yellow light is coming on this micro channel, and then we have a high speed camera. This is a UX Mini 100 high speed camera which uses a CMOS sensor, and it is very compact and light, and this is from LaVision. And then you can see a syringe pump at this side. So when you actually make the flow inside micro channels, you can seed the particles using a seeder particle, and you can actually record at whatever rate you want through using this camera, and this is connected to this PC. Then you can take out the data and process it somewhere in your open source PIV lab or something like that, where you can use the cross correlation technique to get your flow inside the channel. So now we will see how cross correlation works. So as already discussed, like in PTV we were tracking single particles. Here we don't do that exactly, but yeah, we track a group of particles and their interrogation windows. So basically cross correlation is finding how similar two different functions are. We'll do some examples to which will clarify things more. So suppose we have this channel and we have this particles, the seeder particles inside. These are the seeder particles, and we have this channel. And again, so what we do now is we divide this whole flow domain into a number of windows, and these are actually known as the interrogation windows. And these interrogation windows can be of any shape, like this. It can be square, it can be rectangle, it can be circular even. And the best part is you can change the size as needed. I mean, if you have a lot of particles, you can use a smaller window, and if you have if you have less particles, then you can use a bigger window. It actually depends on the requirement of the experiment. That has to be judged very well. In the end of this topic, I'll show you the effect of changing this interrogation window size. So now suppose we have, so you actually have a group of particles inside this interrogation window, and then actually you do the cross correlation for every window which has been actually created here. I mean, if it's like 4 into 8 here, so yeah, 32 windows. For each of the windows you'll be doing the cross correlation at different time instances. So basically the idea is to track a pack of particle motion and not a single one, and then we estimate how much this interrogation window has actually shifted within the recording time delta t, which we can set as needed. So now let's see the idea in a bit more depth. So this is, suppose you have an image, that is I1, and this is an image, and you have some particles here. Obviously I have made kept the particle density very less, but in actual cases the PIV particles are very densely packed to get a better correlation and data. So okay, so now what we do, we have this image 1 at some time t1, and then we divide this image into say 4 interrogation windows like this, right? Now we will just talk about this orange window. Now we have another image I2 which is taken at t2 time, that is basically t2 is nothing but t1 plus some delta t, and now we see how much this orange window has shifted in delta t time. And once actually, so what you can do is you can pick this image, pick this window, and you can try to find the best overlap in this image at t2 time. So basically what you are doing is you are picking one window and you are going at t2 time instance, and then you are trying to find the best overlap between these two. And once you get the best overlap, you actually get a correlation peak, the maximum correlation peak, and using that you can say that how much this the particles have actually displaced. So the basic idea is you take the interrogation window in I1 and overlap it with I2 to find the best overlap, and this best overlap, as I told you, will give a peak and the shift in x and y of this interrogation window, and if you get the x and y shifting values, then you can actually get a vector at the centroid of this interrogation window. So if you are dividing this into 4 parts, then you will get basically 4 vectors at the centroid of each of the interrogation windows. And in practice, cross correlation gives how much windows must be shifted to get the best overlap. Actually, basically how much your windows must be shifted in delta t time to get the best overlap. So what we want to find is the best overlap, and if you get the best overlap, you get a very significant peak, and that gives us the displacement of the windows. So now we will see a simple 1D correlation, cross correlation basically, and how does it work. And we will consider two functions, f of x and f of y, and we will see how we can define the cross correlation function for these two functions. So say this is f of x, and here you can see this is f and this is x, and it's a top hat function, this blue color, and we also define some g of x which is something like this. Okay, now to write the cross correlation, we use this symbol. So basically f cross basically g, and this should be a function of say zeta, and it is actually defined as integral of minus infinity into the whole domain f of x into g of x plus zeta. And actually since we are integrating in say x, so we get a function in terms of zeta. And then if you actually, as we talked about it in the previous slides, that we actually are interested in shifting the interrogation window, and when you shift it you get the displacement in delta x or delta y. So here, since we are just dealing in 1D cross correlation, so we'll get some displacement in x. Now let's displace this first function, and we see that if you displace this the f of x function by zeta, you can write something as the same thing, just that instead of f of x you can write it as f of x minus zeta and g of x into dx. And actually when you do this you get something like this. So if you get, so you can see a pink color function here, which is nothing but the f of x being shifted in basically if I write it something like this, so f of x is shifted by some zeta value, and when you integrate this two thing you get a peak here, right? Now if these two are not overlapping, then you won't get anything. I mean the integral will be 0 and you don't get a peak. That happens when actually your particles move out of the window size, which is very undesirable. However, here you can see you get this, and actually this shift is this value is basically the shift in the function, and this gives you the delta x. So what we did is basically shift one function and then find their products. Say we have shifted this f of x and we have found the product of this f of x minus zeta and g of x, and then you perform the summation or the integral, and the best overlap will give the maximum integral value. and the coordinates of the peak gives the shift in x and y. Since there is no y, so we'll just get a x, how much it has shifted in x. And most of the time we are dealing with images, so we'll have pixels, and instead of integrals we actually use the summation of the functions. We'll talk about it in the next slide. So let us see, the same thing can be actually extended to a 2D cross correlation, where you can write it something like that. If you have f and g cross correlating suppose zeta, and I have taken another variable eta, so you do a double integral over the whole domain, and you can write something like this: f of xy and g of x plus zeta and y plus eta dx dy. Now let us shift. Now, so if you shift in both x and y, then what we can write it is f of x minus zeta and y minus eta and g of x and y, and this should actually give the cross correlation and the shift in both x and y to get the best overlap. Now in terms of pixels, if we have suppose m cross n pixels in an image, then the same thing, the same formula can actually be written as this f and g cross correlating, and we can write it as summation signs instead of integrals, and you have this n is equal to 0 from capital N minus 1 and m is equal to 0 to m minus 1. You write it as f of m and n, g of m plus I and j. So what we say is we are doing the summations over n and m, and we are shifting this image by I and j, and once you shift it, then you take the product of all these two functions, and then basically you are doing the summation over n and m. This gives you the cross correlation peak, which is required to get the vector and the flow field. So cutting a very large story short, PIV, as already told, I mean we are not actually tracking a single particle, and we are actually seeing how a bunch of particles passes through a window, and basically it's a Eulerian method, unlike the PTV, which was normally a Lagrangian way of tracking particles. So here we are doing nothing but searching for a zone in a future frame basically at delta t, and that matches well with the current frame's interrogation window. So to sum up, basically you have a flow field which you have actually divided into here into 4 cross 4 grids. You have particles, and you actually see at some time t you have this pattern like this, and at some time t plus delta t you have this one. And basically I am just showing here for this interrogation window, but what PIV will do is that it will actually try to cross correlate each of these interrogation windows with each other by shifting and by finding the best overlap so basically this is the future frame at delta t, and this is the current frame, and when you actually get these two images, you try to do the cross correlation with these two images, and then you get a peak which looks something like this. This has been taken from Raphael et al. It's an excellent guide for anyone to understand PIV. And then if you get this peak, you get the displacement, and then you get a vector for the interrogation window you are looking into. So as such you will get for this, for if your flow field looks like this, then you should get around 16 vectors for each of the interrogation window you have created. So as I told you, we'll be seeing a very small comparison between like two synthetic images, and to actually investigate how the vectors change if you change the interrogation window size. So what I have done is basically I have considered this synthetic image of a flow field which was actually generated using MATLAB, and MATLAB, the latest version of MATLAB does this. You can actually generate some synthetic images by giving the parameters. So here basically the number of particles it is using to simulate this image is around 1 lakh, and the size of each particle is actually 3 pixels. So yeah, so I have taken this image at some time t, and yeah, so the total pixels is 800 to 600 pixels, and in some time t plus delta t I have generated this image. So these are actually typical images, typical PIV images, and it looks like this. This is very well lit, and you can see the particles very clearly, and the density also, you can, as you can see, that it is very densely packed, and unlike in case of PTV where the particles normally has to be sparsely packed to track them, right? So yeah, and you can see now just by looking at it you won't be able to see the difference, right? I mean because the delta t is very small, and but yeah, if you play it in a pattern on a loop, you can see the particle shifting. Yeah, that should be that can be done. But yeah, now what we do, I'll show you. So here you can see a blue box, and this processing is done using PIV lab in MATLAB. And by the way, now PIV lab is also available as an open source software. They recently released it, so everyone can try this, because yeah, it's a good hands-on, and PIV lab is very well used in the research area, and it's a very well established software and very easy to use also. So here you can see I have created one window size which is of 32 pixels, 32 cross 32 pixels. It's a square box, and here I have created a box which is of size 64 into 64 pixels, and we'll see when you actually do the cross correlation and PIV between these two images, how basically not between these two images, basically the previous two images, you will see the difference in the vectors. So for 32 cross 32 basically you get something like this. So as I told you, I generated a synthetic image, so you don't expect it to be like a parabolic profile which normally our intuition says. This was just a linear shift of the particles in y direction, so you can see it's giving a uniform shift almost everywhere. And when you, for 64 pixels, you can see the vectors are very sparsely like aligned. I mean they are aligned and they are very sparsely packed, right? So this is what changes when you actually change the window size, because you are dividing the whole image into much lesser grids now, and hence you get lesser number of arrows. And actually it depends on your need as to how you want to actually present your data. And also it's very so here actually I have generated a synthetic image, so you can play with the image and you can get very nice these kind of vectors. But in real life scenario, when you are doing experiments, it is very important to basically take into account the particle density, the lighting actually, because normally lighting plays a very important role in PIV, because we normally use lasers, and which is not very necessary, but yeah, we use lasers for this, and the intensity and the depth of the laser and those things should be very well known from before, so that your particles are very well lit and you can actually get such good vectors without much noise, right? So yeah, you can actually go much lesser. You can go to 12 pixels and those kind of things to get much more closely packed vectors. But yeah, it will start giving erroneous results if the particle density is not very high, and if you keep on going to a very smaller size of window, you will start getting something erroneous which won't make any sense. Yeah, okay.